And now I'll just give you some examples where we use this and try to figure out what we can get out of these things. All right, so we're back to our friendly equation, par C, first term to 0, second term to 0, last term to 0. We restrict to par C, par T, first order rate constants. Okay, so we did some controlled diet experiments, and here's one of the experiments. We just changed from a C3 to a C4 hay, and then after 150 days, we switch it back to the original diet, and then we just put a little spike at the end just as an isotope marker. And then Linda Aliff cut the horsetail hair up to about every 1 millimeter. They grow at about rates of about 1 millimeter a day, and that's enough to get a nice isotope analysis. So some of the team that we had, we worked with other animals. We worked with rabbits. This rabbit actually had diabetes, and we learned how to identify diabetes using stable isotopes, which had never been done before. Some labeling problems, but so it goes. Okay. Huh? Yeah, we had an 8-year-old assistant who was allowed to name all the animals, and he thought that would be nice to name pig, cow, and cow, pig. Okay, here's our data. Well, actually, here's the experiment. Is the diet, feed it a pure C4 diet, okay, then switch the diet, and then back to C3 diet, little spike at the end. The dotted line here is the instantaneous equilibrium value that we know it should have based on the isotope enrichment. So it should be 3 per mil enriched from diet to horse hair, right? So this is what it should be. Now the dots are our data, and you can see that we make the diet switch, and in 1 day it gets halfway to the final. So to the final value, so you might think, oh good, well then this is really great. We've got, in 2 days it should get half of the half, then the next half, and in 3 days, the third half, so we should actually come to equilibrium in about 6 days. But it doesn't, it slows down somehow. And you see that even after 150 days, we're still not yet to equilibrium. Equilibrium is way up here, so we may have to go all the way, like we should have done a 3-year experiment here. Okay, well, we can recast this in our isotope space and try to figure out what the hell is going on. This is our longest isotope pool. Okay, so this is our natural log space, and we can see that's pretty much a straight line. And so what it says is, and this intercept is the fractional contribution to the whole process. So he's find is something has a half-life of 138 days, and it represents 44% of the total contribution. And what we find is there are 3 isotope pools. One is pretty small, just 10 or 15%, but basically what it means is half of the stable isotopes that show up in your hair have a very long residence time, a half-life, and the other half has a half-life of basically 1 day. So what's in your hair today, half of the isotopes going into your hair today, half of that is what you ate yesterday, and the other half is your average diet over the last year. Okay? So there's this modulation, attenuation of your diet. Now in Seth's talk after the coffee break, you will see that what goes into protein tissues has a lot of different components. Okay? So hair is made up of what, Seth? 30 different amino acids, okay, of which 15 make up most of the mass. Well, some of those, each of those probably has its own individual half-life. And so Seth is going to describe why, I think he's going to describe why some of those may be expected to change very rapidly, and because they may be essential and or non-essential. non-essential. And the other half are the other one. It always gets complicated when you make up things while you're talking. You say the wrong thing. You have only two choices and you get confused. So the other nice thing about this forward model is that if you look at the individual pieces, you can say that, well, the delta value at any time is related to yesterday, okay, what the value was yesterday and the difference in time between our two measurements, and then the diet contribution. And we can do this for every one of the pools, and so if we have a multiple pool system, we can combine all of this stuff, and it just represents an equation where every single pool, you see, has a diet term in it, and then we can recombine everything. And so it just says that if you have a diet sequence of a tissue like hair that can be described with this first order reaction kinetics, you can actually back out the diet using every individual hair segment. The only one you can't do is the first one. But you can do all the other ones really quite well. So with our elephant hair, we have 100 samples, and for everything except for the very first sample, we can calculate the values. And we can make a pretty good guess at the very first sample. So this is some different horses that we did in which we thought, okay, well, let's apply the model. So here's just, again, some horses that we had a 7-day switch in, and we chop up the tail hair, that's these white dots, and the black represents what we calculate the instantaneous diet was based on the isotope sequence. And we'll just fit it with a 3-pool model using this other data that we'd collected, and we'll just do it with a 1-pool exponential fit, which is the previous way of doing it. And you can see that this really does a good job at fitting, it's not a perfect model, but it fits the data really well, and especially hits the initial and final conditions very, very well, whereas this 1-pool model misses the initial value and misses the final value, has a terrific overshoot that's like 7 or 8 per mil off. And so what we want to do then is then apply this to some real systems. Okay? So this is just an example where when we worked this out, I wrote to an unknown person who later became a colleague, said, "Dear Ian, I know you knock down elephants to put GPS collars on them. Next time, see about collecting a tail hair." And so since then, the Kenya Wildlife Service and Save the Elephants has this as a standard protocol because they were collecting other tissues. They collect blood samples, they collect all sorts of other things, and a tail hair sample was something that they could easily work into their normal protocol. And I said, and we'll tell you some cool diet things. So this is the tail hairs on an elephant's. They grow at about a little less than 1 millimeter a day, and it's about 1 milligram worth of material, so it's an enormous amount of material. And this is an elephant wearing a GPS collar. So the transmitter's up there, and this big thing is a lead weight that holds the collar down below his neck, so the receiver's always pointed upwards. This is just some initial data to show how we actually get the growth rates of the hair. So we have 4 different hairs represented here from 2 different animals. Queen Elizabeth was the mother of Anastasia, and everybody else in that family has the name of some queen at some point in history, family known as the Royals. So we have a sample collected here, 7 July. Actually, that was the animal when this individual died. We collected a sample from her daughter, 9th of July 2001, 25th of March 2002, And we actually have data all the way out over to here, to 2016. And George should be trying to see if we can get a sample from 2017. So at this point, we have almost a 20-year history from this individual family. So what can you do with this? This is something called NDVI, which is the Normalized Difference Vegetation Index. And basically, high is green, down is brown. Okay, so this is just a measure of the incoming versus the outgoing solar radiation, or solar and earth radiation. And this is rainy season, dry season, rainy season. So in Kenya, there are 2 rainy seasons a year. And this is an area known as Samburu. So this shaded in area represents the average delta C13 value and calculated diet for 5 different resident elephants, but each of which represents a different family. Okay, so we're trying to characterize what are all the animals in this park doing. And we also showed that the 2 sisters living together have almost identical diets. We really can't distinguish the isotope value on any in 2 hairs collected on the same day from these 2 different animals. So this is the diet, and you can see dry season mostly C3, wet season C4, C3, C4, C3, C4, kind of nice. So we could quantify things. Then I analyzed another sample, and I wrote to George, and I said, George, this is a really weird sample. So this is the nitrogen isotopes, and the 5 families, you see, have a very constant value. They're living in the Samburu Reserve, which is a desert. And this animal, this other animal, has a very low value, abruptly switches to a high value, then low, then high, then low, then high. What the heck is going on with this individual, B1007, also known as Lewis? It's a male, Lewis. Well, we think he's a geologist because the geologists have reputations for during going to their mountain meadow to do their work part of the year. And so what this individual is doing, we knew from the GPS collar he was wearing, in the dry season, he's on Mount Kenya. In the wet season, he goes down looking for his lady friends, and he goes down to the desert. Next dry season, back up to the mountains to his mountain meadow where it's nice and cool, and he has to do his field work. Okay? Next time the ladies all show up, go back and look for the ladies. Okay? So, but Lewis's diet, you can see, when he's on the mountain, he's eating C3 plants, and then when he goes down to the desert, he's eating C4 plants, C3 plants, C4 plants. But here he's on the mountain. We know he's on the mountain because that's his nitrogen values, that's a mountain value. But he's eating an enormous amount of C4 plants, and there aren't any C4 plants growing on the mountain. So what in the world can happen to this guy? And this is the distance which we're talking about. So 40 kilometers is the distance. It was described as streaking, and it's just because he literally streaks from one place to another. This is done in about 8 hours at night. So 40 kilometers, that's a big distance. So I just want to show you the track that he takes here. Okay, we know, we get readings from this guy every 15 minutes, so we know where he is. Okay, this is the track that he was following, you see? Okay, he did not make that track. Okay, but all of this is farmland, and if he's caught in the daytime in the farmland, he'll be shot. Okay, and in fact, that's how he eventually died. So here is Lewis. Here's the forest boundary when he's living in the forest, and so the GPS tells you some very interesting things. So the question is, how many hours? Which hour of the day is he outside of the Amenti forest? Okay, daytime, well, noon, he's inside the forest. 6 in the evening when it gets dark, inside the forest. He leaves when everybody goes to bed. That's when he leaves. He goes out of the forest, and here he is at night outside the forest, okay? But by 6 in the morning when the sun comes up, I'm a good little elephant, you know, I'm just in the forest. Don't think about me. Okay, well, outside the forest it looks like this, okay? Inside the forest it looks like this. Okay, very different ecosystems. So, let's look at that window. Over a almost 2-month period, 38% C4 in his diet. Okay, looking at the previous figure, what percentage of the day was he outside the Amenti forest? Close to 38%. Okay, this is the C4 grass that he was eating. He was finding C4 up on the mountains, but it was all the stuff outside. And so this was the first time in which you could actually quantify for, you know, years and years. They say, oh, that guy's a crop raider. Oh, well, Kenya Wildlife Service would say, well, he doesn't eat much of your stuff. Well, we can say, this guy was eating 40% corn, okay, for 2 months, and that we can actually quantify the damage that those particular elephants were causing. And we didn't need to sample the elephant every single day. Another possibility might have been you might have been able to get dung from these animals, but it's really hard. These guys are moving a lot, and you wouldn't necessarily know which animal. And there's only a few animals that are the crop raiders. Okay? I'm always asked about how do you collect elephant hair? Well, you have to knock them down. I mean, and then you can do it. This is just one of my field assistants who got all dressed because he also worked for a tourist company. George Whittemire, the principal colleague working with on this, had a different way. He was in this truck, actually, when it was destroyed by that particular elephant. And George lived to come and take this course. So, all right.